minus 273 degrees Celsius, at a fraction of a degree above absolute zero, inside a dilution refrigerator at the Rutherford Appleton Laboratory, a tiny crystal of cobalt niobate stops behaving like a normal magnet. The atomic spins within this common metal suddenly align in a sequence perfectly mirroring the golden ratio. I am Dr. Sarah Jenkins. We are bypassing the chemistry of cobalt to examine its quantum physics. From the 2010 discovery of 248-dimensional E8 symmetry hiding in its spin chains, to recent breakthroughs in cobalt-based Kagome lattices acting as superhighways for massless electrons, cobalt is proving to be radically weird. That 2010 experiment by Radu Coldea fundamentally changed how we view cobalt. In cobalt niobate, the magnetic cobalt ions form long, isolated, one-dimensional chains. It is a classic Ising ferromagnet. But when we apply a transverse magnetic field of exactly 5.5 Tesla, we push the crystal to quantum criticality. At this tipping point, the electron spins behave like plucked guitar strings, vibrating in quantum resonance. When we measured the frequencies of the first two resonant notes using neutron scattering, their ratio was exactly 1.618, the golden ratio. That mathematical elegance isn't just a cryogenic parlor trick, Kwame. It translates into real-world topological materials. For decades, engineers just saw cobalt as a rigid ferromagnetic layer for hard drives. But when you arrange cobalt atoms into a Kagome lattice, a pattern of corner-sharing triangles resembling Japanese bamboo weaving, the physics completely inverts. In 2019, we synthesized a cobalt-tin-sulfur compound, CO3SN2S2. Within this specific geometry, the magnetic field doesn't just align spins, it forces the electrons into a topological state. They become whale fermions. Exactly, May. The Kagome geometry creates what we call geometric frustration. The electron wave functions are trapped, unable to settle into a simple low-energy state. This generates an intense, localized Berry curvature. To put that into perspective, the Berry curvature in these cobalt crystals acts like a synthetic magnetic field of hundreds of Tesla, far stronger than any physical magnet we can build. In the lab, this manifests as an anomalous Hall conductivity peaking at 1,130 inverse ohm centimeters. The technological implications of that zero momentum loss are staggering. Right now, conventional copper wiring and silicon transistors rely on electrons crashing through atomic lattices. They scatter, they generate heat, and they waste energy. Data centers currently consume over 2% of global electricity just fighting this electrical friction. By utilizing the whale fermion pathways inside these topological cobalt crystals, we can protect the electron spin state. Let's ground this in the physical reality of the laboratory. We are talking about the exact same atomic element used for centuries to tint glass blue and currently mined by the ton to stabilize lithium-ion smartphone batteries. May, when you need to study these massless whale fermions, you can't just buy a topological Kagome crystal off a commercial supplier's shelf. How do you actually grow a cobalt-tin-sulfur compound from scratch? What does that synthesis process look, smell, and sound like when you are standing at the workbench in your MIT materials lab? It requires a technique called chemical vapor transport. I start by measuring out high-purity cobalt, tin, and sulfur powders inside an argon-filled glove box to prevent oxidation. I seal these powders into a thick quartz ampule, pulling a hard vacuum of 10 to the minus 6 torr. Then it goes into a dual-zone tube furnace. We establish a steep temperature gradient, dropping from 900 to 800 degrees Celsius, and hold it there for 2 agonizing weeks. We use iodine gas as a transport agent. Slowly, atom by atom, the vapor drifts to the cooler end of the tube, depositing perfectly hexagonal, highly reflective metallic crystals. That collision of raw metallurgy and elegant mathematics is exactly why this field is moving so fast. 3 takeaways from today's panel. First, cobalt's one-dimensional spin chains physically manifest the 248-dimensional E8 symmetry, bridging string theory and solid-state physics. Second, arranging cobalt into a Kagome lattice forces electrons to behave as massless whale fermions, moving near the speed of light. Finally, these topological superhighways could eliminate electrical friction, paving the way for zero-loss spintronic computers. Thank you to Dr. Kwame Osei and Dr. May Lin for joining me at the bleeding edge of the periodic table.